Hello everybody. This video is interested in multiple unit process calculation that's be done by the following. For each multiple unit process systems, there are some of a problem solving strategy that we should follow it to find all our calculation. Here is a 7-step plan for approaching mass conservation problem. The first one is to draw a problem sketch with create list of items for possible inclusion in sketch. Then we should define the system boundary, the time period or the basis as we know, and then the extensive properties to be counted. Thirdly, make an accounting table. Define a math problem from step 3. This may be a system of algebraic or ordinary differential equations as appreciate of the problem. Evaluate uniqueness and extents of a solution for the math problem. Example with a degree of freedom analysis. Fifth, if a step 4 doesn't provide a well-defined math problem, reconsider step 1 to 4 and or assess whether additional information must be included, such as process constraints, material property, and etc. And then we should solve our math problem, and finally reality check, does the solution make physical sense or not. In our example, we have here two distillation columns in series. Two separation columns in sequence are used to separate the component of a feed consisting of 30% of benzene, 55 toluene, and 15 xylene. The analysis of the overhead streams from the first column yields 94.4% of benzene, 4.54 toluene, and 1.06 of xylene. The second column is designed to recover 92% of the toluene in the original feed in its overhead stream at composition of 0.946. The bottoms are intended to contain 92.6% of xylene in the original feed at a composition of 0.776. Here we are interested in compute the composition of all stream. So these are the steps that we will follow it to find our solution. Our examples have two distillation columns in series. So our question is, two separation columns in sequence are used to separate the component of a feed consisting of the following. So first we have two distillations column in series. So a feed consisting of 0.3% of benzene. So the composition of the feed 0.3% of benzene and 55% of the toluene, and the rest, which is equal to 0.15 for the xylene. The analysis of the overhead stream from the first column. So this will be m.1, and here we have m.2, which is the overhead of the distillation 1, and here we have distillation 2. Of the overhead stream from the first column yields 94.4% of the benzene, so 0.944 of benzene, and 0.0454 for the toluene, and the rest which is equal to 0.0106 for the xylene. The second column is designed to recover 92% of the toluene in the original feed in its overhead stream at the composition of 0.946. So the overhead of the second distillation column will consist of 0.946 of toluene. So we don't know the composition of benzene here, which is in stream 4, and we have here stream 3, and here we have stream 5. The bottoms are intended to contain 92.6% of xylene in the original feed at composition of 0.776, and they need from us to compute the composition of all stream. So the bottom of the second distillation column will consist 0.776 composition of xylene in that stream. So here we will have a composition of benzene in the fifth stream, which is unknown, and here which is unknown, in addition to the mass flow rate of all streams. Then the first step that we should to put it is to draw a table of degree of freedom analysis. So the degree of freedom analysis is summarized at that following table that I will make. So first thing we have number of unknowns and number of independent equations, also the number of relations that can we have it in our system, and finally we have the degree of freedom. But first of all, we should know how many systems that we have in our problem. First of all, we have the first distillation column. This will be our first system, and also the second distillation column, and finally we have overall process system, which is consistent for all that stream without the mass flow rate of the third stream that's in between of the two distillation column. So we have 3 systems for the first distillation column, and for the second distillation column, and for overall system. First of all, if we know how many unknowns in the first distillation column, we don't have the mass flow rate for the first stream, in addition to this one and this one, and the composition of these 3 components in the mass flow rate of the third one. So X for benzene in the third one, we don't know it, and also for the toluene we don't know it, also for the xylene in the third one we don't know it. So we will consider these 3 unknowns in addition to the mass flow rate for the second one and the first one to be 5 unknowns. So we have 5 unknowns here. And the number of independent equation is related to how many components that we have. We have 3 components, so we have 3 independent equations, and we don't have any relations here. So the degree of freedom 5 minus 3, which will equal to 2. And for the second distillation column, we have 3 unknowns here, and here we have, in addition to that, this unknown 3, 4, and 5, and we have here 6, and we have here 7. So we have 7 unknowns, and the number of independent equation will equal to the number of the components, which is equal to 3, and we don't have also here any relation, so we'll be left with a result of 7 minus 3 will equal to 4. And for the overall system process, how many unknowns that we have? We have here 1 unknown, and this the second one, the third one, and the fourth one, and the 5 and 6. We have 6 unknowns, and the number of independent equation, as we said at these 2 before, which is equal to the number of components, so which equal to 3. But the most different thing in that situation and in that step, that we have 2 relations for the amount of the toluene and xylene for the overall process. So we have here 2 relations, then we will end up with 1 degree freedom. But we can consider our bases which equal to 100. So if we consider our bases which equal to 100 kilogram per hour, we will reduce the number of unknowns in the overall process to 5, because we will know here that will equal to 100 kilogram per hour. So it will reduce to 5 unknowns. So 5 minus 3 minus 2 will end up with 0. So we always start with the least number of degree of freedom, which is here the overall system. Secondly, after we draw a table of degree of freedom for that process, we assumed a basis of 100 kilogram. So our basis will equal to 100 kilogram per hour. So according to that, this basis will reduce the degree of freedom for overall process to 0. So we will start with our system, which is the overall process. Then we can make overall process balance for the total mass and component mass balance. So for the total mass balance, we have our basis which relating to the mass flow rate of stream 1, which will equal to the mass flow rate for stream 2 plus mass flow rate for stream 4 plus the mass flow rate for stream 5. Then we have a component mass balance. Component mass balance. We have 3 components, which is the benzene and the toluene and the xylene. For each one we will make a component mass balance, which equal the composition of the benzene in the first stream equal 0.3 times 100 equal to 0.994 times mass flow rate of stream 2 plus the composition of benzene in stream 2 time the mass flow rate of stream 4 plus the composition of benzene in stream 5 time mass flow rate of stream 5. Then for the toluene, we have a composition equal 0.55 in the first stream, which will equal to 0.0454 times mass flow rate of stream 2 plus 0.946 times the mass flow rate of stream 4 plus the rest of the composition, which equal 1 minus 0.776 minus the composition of the benzene in the fifth streams. This all to the mass flow rate of the fifth stream. To the xylene, we have a composition which equal to 0.15 times the mass flow rate of the first stream, and this all equal to 0.0106 times the mass flow rate of stream 2 plus 1 minus 0.946 minus the composition of the benzene in the fourth stream. This all to the mass flow rate of the of stream 4 plus 0.776, this all to the mass flow rate of the fifth stream. So, after the analysis of the overall process, we now consider our unknowns that we should have to find it, which is the mass flow rate of stream 2 and 4 and 5, and also the composition of the benzene in the fourth and fifth streams. Thirdly, after we doing the analysis, we should consider our relations. We have two relations in our overall system. In the problem, they said that the second column is designed to recover 92% of the toluene in the original feed in its overhead stream. So from that we can do that relation. So 92% of the toluene in its original amount in the feed equal to its composition in the fourth stream, which equal to 0.946 times the mass flow rate of the stream 4. So from this relation we can find the mass flow rate for the first stream, and after calculations it's equal to 53.5 kilogram per hour. So from the first relation we find the mass flow rate of the fourth stream, which is equal to 53.5 kilogram per hour. After that, they said also that the bottom stream of the second column is intended to recover 92.6% of xylene in the fresh feed. So that second relation said that 92.6% of xylene in the original fresh feed, which is equal to 0.15 times 100, will equal to its composition in the fifth stream. So here we can find the mass flow rate of the fifth stream from our calculation, which will be equal to 17.9 kilogram per hour. After our calculation, we can now consider that the total mass balance equal to 100. This all equal to mass flow rate of stream 2 plus the mass flow rate of stream 4 plus the mass flow rate of stream 5. Of course, that's for the overall process. We find this one and this one, so here we can find the mass flow rate of stream 2. So the mass flow rate of stream 2 will equal the mass flow rate of the fresh feed minus these two values, which equal the mass flow rate of the stream 4, which equal to 53.5 plus 17.9 kilogram per hour, which is equal to the mass flow rate of the stream 5, and these all equal to 28.6 kilogram per hour. So after this step, we now find all the mass flow rate of all streams. So now we can find the composition referring to our component mass balance for each component. Finally, after finding the all mass flow rates for all streams, we can now back for the component mass balance for the toluene and benzene to find the composition of the benzene in the fourth and fifth stream. So for the toluene, we know that it's the mass component balance equal to that equation. So we find the mass flow rate of stream 2 and stream 4 and stream 5. So our unknown is only the composition of the benzene in the fifth stream, which after calculation we can find it equal to 0.051. And after that, when we come back for the component mass balance for the benzene to find the composition of it in the fourth stream. We know we find now the composition of the benzene in the fifth stream, and also we know these three variables. So the rest we will find the composition of the benzene in the fourth stream, which will be equal to 0.04.